voltando a aparecer novamente. Nós vamos começar com o Ricardo, com o Rogério, desculpe, com o Rodrigo Nemmen, que vai falar sobre o próximo Massive Black Holes em estudo em Gamma Rays. Eu acho que você pode começar em inglês.
Okay. Thank you very much for the kind introduction, Marcio. My name is Ricardo Rogério Rodrigo Nemmen. I would like to thank the organizers for the.
Marcio is actually Marcos.
So thank you, Rogério, for the invitation. So today I would like to tell you some of the work that my group is doing in the context of the Fermi LAT collaboration. And my phone is ringing right now, so let me disconnect my phone. I can't disconnect my phone. And just before proceeding, since this is a workshop in honor of the great Reuven Opher, I don't know how to pronounce his first name. I just wanted to share a story that happened right after I moved to São Paulo. So I was working in the United States, and then I moved to São Paulo to begin my faculty position here. And so I remember kindly that right after I moved to São Paulo, so Opher contacted me because he was a faculty here. He was a retired faculty here in IAG-USP. And then I remember, so I was just starting to set up the journal club, the Black Hole Journal Club here. We didn't have a Black Hole Journal Club. Well, we didn't have a journal club at all in the department. So I set up a Black Hole Journal, a thematic Black Hole Journal Club. And Opher found out about this journal club, and then he contacted. He was living in New York, right? And then he contacted me. Hey, Rodrigo, I would love to attend the journal club meetings. The new meetings that you are setting up in your journal club. And I was surprised, and I was happy and surprised, and also with an admiration for Opher, because you see this retired faculty in his mid-80s. And still having interest in keeping up with the literature in the black hole field, and he didn't need to attend the journal club meetings, but he was attending over. I believe we were using Zoom. This was before the pandemic times. This was in 2015. So this really, I really have a lot of admiration and deeply miss Opher, and I was really admiring his strength in attending, his interest and persistence in attending many journal club meetings remotely. Anyway, so after this little story, let me proceed. So I wanted to begin by showing you the all sky image of our taken with the Fermi Large Area Telescope. So for those of you that are not aware, the Fermi telescope is a telescope that is around our planet for over 10 years, and it's taking images, light curves and spectra of the sky in gamma rays. And here we see some of the main sources that have been observed in gamma rays with the Fermi telescope. I will talk a bit more about some of the sources. And this image actually was assembled by my group. So it looks like an optical image of the sky, but it is actually a gamma ray image. So let me talk about the culprits of this talk, the main actors. Let me begin by talking a bit about Sagittarius A star. So Sagittarius A star is the nearest supermassive black hole to our planet. It's located in the center of our galaxy. And here we can see some of the stellar orbits around this supermassive black hole, including one of the closest stars to the black hole, the star S2. And in comparison, you can see at the bottom right corner of this image, you can see that the size of in the same scale of the stellar orbits, we can see the orbits of some bodies in our solar system at the same scale for comparison. And whereas S2, it has a similar size of the orbit to the Sedna, the small body of our solar system, Sedna. The size of the orbits are very similar. So Sedna takes about 20,000 years to complete a full orbit, whereas S2 takes only 15 years to complete a similar sized orbit. And this really gives us an idea of how massive Sagittarius A star must be. And in fact, the black hole mass is 4 million solar masses, and it's located at 8 kiloparsecs distance. And just for here I'm comparing the Schwarzschild radius of Sagittarius A star in comparison with the Sun. So the Sun, our Sun is tiny in comparison with Sagittarius A star event horizon. Of course, the gravitational potential is vastly larger near the event horizon Sagittarius A star, and this is one of the main reasons why we love black holes so much, because they allow us to probe unexplored regimes of space-time curvature, unexplored here on our planet, of course. Let me finish. Well, this is a recipe. If you want to create a 10 to the 8 solar masses black hole, you just need to fill with, if we had the resources, if you were Elon Musk or Jeff Bezos and you had the resources and the money to do this, this is a recipe to create a 100 million solar masses black hole. You just fill up with water a sphere with the radius, with a radius larger than the distance between the Sun and our planet, and then you will create a 10 to the 8 solar masses black hole. Okay, but coming back to Sagittarius A star, Sagittarius A star has a profoundly non-thermal spectrum. Here I'm showing you the electromagnetic spectrum coming from the center of our galaxy, from radio to X-rays, and we can see here synchrotron emission from thermal and non-thermal electrons. We can see inverse Compton scattering. We can see Bremsstrahlung. The point being that the spectrum is non-thermal. It tells us that there is a weak non-thermal source at our galactic center, and the source is associated with the supermassive black hole, the Sagittarius A star, but it is not the black hole. This is not Hawking radiation, okay? Don't get excited, okay? This is the electromagnetic emission from gas falling onto the black hole in a kind of a structure, in a kind of a flow that we call radiatively inefficient accretion flow, which is the sort of spiraling inflow that you get close to the event horizon when you throw matter, when you throw, let's say, hydrogen, when you throw hydrogen into a black hole, it gets accelerated, it gets heated up, it gets ionized, and then you get a very hot, radiatively inefficient accretion flow, where the cooling time it's much larger than the time for the particles to fall into the event horizon. So you have this sort of structure. And Sagittarius A star is, of course, a primary target for the Event Horizon Telescope. We have already imaged the event horizon, the shadow of the event horizon in M87, and now there are rumors that the Event Horizon Telescope collaboration is working on the next set of papers reporting the next EHT result for Sagittarius A star. Since I'm not a member of the Event Horizon Telescope collaboration, I can mention this rumor here. The point being that because of the Event Horizon Telescope observations, this triggered a rapid and intense development in the theory of Ryevs, in the theory of the sort of hot flows that I just mentioned here. And Sagittarius A star is just one example of a vast class of astronomical sources that we call low luminosity active galactic nuclei. Okay, low luminosity active galactic nuclei. I will abbreviate this class of sources with the abbreviation LLAGN. There is besides Sagittarius A star, there is another very famous low luminosity AGN, which is M87, the black hole that was imaged in 2019 with the Event Horizon Telescope. Low luminosity AGNs are very interesting in astronomy and high energy astrophysics because they allow us to probe black hole physics at the sort of regimes where the event horizon is underfed with matter. The sort of plasma physics, which consists of collisionless to temperature plasma physics. Of course, low luminosity AGNs are important because the nearest massive black holes to our planet are low luminosity AGNs. This sort of source is found in half of nearby galaxies, in the centers of half of nearby galaxies. And they likely, for astronomers, low luminosity AGNs are important because through this sort of phenomena, the black hole can produce very strong winds or outflows, and these winds can transfer energy from deeply in the potential of the black hole. Through these winds, the black hole transfers energy from the strong field regime of gravity to the weak regime on galaxy scales, where the winds can affect the thermodynamics of whole galaxies and galaxy clusters. So this is the reason why these phenomena are physically very important and cherished for astronomers. Some of the open questions around low luminosity AGNs, and in particular Sagittarius A star. Some of the questions, the most important questions: what is the nature of particle acceleration? Why are those known thermal distributions being generated? What is the nature of the high energy emission that we see here on our planet from these sources? Are we seeing X-rays and gamma rays coming from what part of the flow? Are we seeing them from outflowing relativistic jets, or are we seeing them from the accretion disk? And moreover, is this emission due to leptonic processes, or is this emission due to hadronic or due to hadrons? What is the source of the variability in the spectrum that we see in gamma rays in particular, because this is a gamma ray talk, so I will focus really on gamma ray emission. And what is the relationship between what is outflowing from the black hole and what is flowing in? In other words, what's the relationship between the jet and the disk? These issues are not explored at all, they were not, let me correct my previous sentence. These issues were not well explored in gamma rays before the work led by my group in the context of the Fermi LAT collaboration. And the reason is that the community, the high energy astrophysics community, is biased towards blazars. So the community is affected by a blazer chauvinism, and I'm trying to change that. I'm trying to shed light literally on the other sorts of black holes besides blazars. And this talk, and I'm not sure how long I'll be able to talk about the actual results, but this talk I will try to give you some a brief overview of the results that my group is obtaining with the Fermi LAT Gamma Ray Observatory for low luminosity AGNs and Sagittarius A star. Let me say a few words about the instrument. There are two types of gamma ray observatories. There is for very high energies above 1 TeV. When we are dealing with photons with above 1 TeV of energy, we use ground-based observatories which use the Cherenkov radiation, and they are indirectly detecting gamma rays. And here are some examples. One famous example is the CTA, the Cherenkov Telescope Array. You will hear at least one talk in this event, I believe on Thursday or perhaps Friday, about the CTA. And we have, for low energy gamma ray photons, we use space-based techniques, which are direct detection techniques based on particle physics, based on techniques of from the particle physics community. And this is the arena of the Fermi Gamma Ray Telescope, which is observing photons with energies between 20 MeV up to 300 GeV. The interesting thing is that Fermi has been covering the whole sky every 3 hours in gamma rays. And because here in the audience we have some people which are involved in the Vera Rubin Observatory, which was called LSST. Fermi is already the LSST of the high energy sky. Fermi is already has been making real-time movies of the whole sky, but in gamma rays. So it's a profoundly important instrument for the high energy astrophysics community. Here is a highlight of the discoveries over the last 10 years. I repeat, Fermi has been in orbit around our planet since 2008. So over these 12 years, there have been extremely important discoveries. Some of the highlights are one of the most important observations behind the birth of observational multi-messenger astronomy, which is the observation of gamma rays from the GW 170817, where we saw gamma rays with the GBM instrument aboard Fermi, and we saw gravitational waves from this event with the LIGO Virgo Observatory. Another very important result, crucial result behind multi-messenger astronomy is the simultaneous detection of gamma rays from the Blazer Texas 0506 and neutrinos that were observed from the same source with the IceCube Observatory. So Fermi is a deeply important observatory for multi-messenger astronomy. But let me skip some of these slides. Here is the Fermi gamma ray sky after this. So this is wrong. This is not 7 years. This is after 10 years of observations. This is the image that my group assembled from the photons of the Fermi Observatory. We can see bubbles, which are probably an outflow of energy and matter from Sagittarius A star. But the scientific targets here are Sagittarius A star in the center of our galaxy and low luminosity AGNs, which are scattered in this fashion here, because they were observed from the northern hemisphere with a Palomar sample, and we were tracking the sources with Fermi as well. It's a sample of about 200 low luminosity AGNs. So let me give you some of the results in observing this Sagittarius A star and low luminosity AGNs with Fermi. And this is the result from my former PhD student, Fabio Cafardo, which is now in the Netherlands, and my current master's student, Lucas Ciconato, which is carrying on this complicated and time-consuming analysis of Sagittarius A star. So my former student, Fabio Cafardo, he found out that there is a very strong Fermi source at the center of our galaxy. The source is the source is significant above background with an 81 sigma significance. So it's a very, very bright gamma ray source, which is at the center of our galaxy. So immediately we were suspecting that this is related to Sagittarius A star. So one of the things that Fabio did is that he did a very elaborate analysis of the emission from the center of our galaxy, taking into account background, taking into account the most updated catalyst or known sources around Sagittarius A star, because the spatial resolution of Fermi is terrible when you compare it with optical telescopes, but it's it's amazing for high energy astrophysics standards. Fabio was able to measure precisely the luminosity of the source. And it's very interesting that the gamma ray luminosity of this point source at the center of our galaxy is very similar to the luminosity of Sagittarius A star from radio to X-rays. And we computed, we estimated that the chance coincidence of this similarity in luminosities is very low, of course, assuming a distance of 8 kiloparsecs to the gamma ray source. So this is an important evidence that the gamma ray source that Fermi is seeing at the center of our galaxy is physically associated with Sagittarius A star. This is another result from Fabio's PhD thesis. He looked at the light curve over the last 10 years for the center of our galaxy. And unfortunately, there is very little strong variability in the light curve observed with Fermi. There are some, we cannot really call this flares, but very little mini, tiny nano flares happening in gamma rays from the center of our galaxy, which seem to constrain the size of the gamma ray emitting region to be within 10,000 Schwarzschild radii, which is more or less the size of the gravitational sphere of influence of Sagittarius A star. Stay tuned for very exciting.
Rodrigo, just a reminder, in my new chronometer here, you have 5 more minutes.
5 more minutes, excellent. So stay tuned for exciting results that we will make public very soon, led by my student Lucas Iconato. Lucas is carrying on the work by Fabio. Lucas is analyzing the spectrum of this central source and also modeling the source. And we have a very exciting result in the works where we found evidence for hadronic emission from the center of our galaxy. This work is under wraps currently, but we hope to share with the community very soon the result. And also, I would like to give you a 3 minutes of review of the results by my other former PhD student, Ranieri de Menezes. So Ranieri analyzed the gamma ray emission from all these low luminosity AGNs. And strangely enough, he found that only 4 sources among the about 200 low luminosity AGNs, they are strong gamma ray emitters. And also the same sources that are very bright in gamma rays, they have kiloparsec scale radio jets. So Ranieri correlated the gamma ray luminosities with radio, and he found that only the radio brightest are detected in gamma. But most of the X-ray bright sources are not detected in gamma rays. So we are hypothesizing that the gamma rays in low luminosity AGNs are coming from the jet, not the accretion flow, contrary to claims from other authors in the literature. So this is a picture for the origin of high energy emission in low luminosity AGNs. So please have a look at the De Menezes et al. 2020 paper where Ranieri modeled in detail the spectral energy distribution of the sources. Let me just finish my talk by mentioning that I just gave you a tiny overview of the work that my group is doing. We have many students, many graduate students in my group. Please go to blackholegroup.org. Here I'm showing you what I call the Einstein's ruler, which is a logarithmic ruler of the distance from the central black hole in a typical galaxy, in a typical active galactic nuclei. We have a vast range of interesting physics here shown on top of the Einstein's ruler. And this is the distribution of my team on the Einstein's ruler. So currently most of half of the team is working very close to the event horizon, but not inside the event horizon. Okay, so we are safely outside the irrationality horizon here. And also half of my team is working far away from the event horizon, and the part of the team working far away is doing mostly phenomenology, is working with mostly Fermi LAT observations, but also optical observations. And here is a summary of the work. So in brief, this is the take-home messages. We saw a gamma ray point source at the center of our galaxy, which is consistent with being associated with Sagittarius A star. The gamma ray emission probably comes from the hot accretion flow or from the base of the jet. This is ongoing work. Stay tuned to the work of Lucas Ciconato. And we also analyzed a whole population of low luminosity AGNs with Fermi LAT. And we found out that only the radio brightest sources are detected in gamma rays. And we believe that there is a different origin for the gamma ray and radio electromagnetic emission. This is coming from the jet, from the outflow, from the relativistic jet, versus the X-rays, where the X-rays are coming probably from the accretion flow. So stay tuned for for more papers reporting some of these results coming soon. Thank you very much.
Thank you. Thank you very much for such a beautiful talk, especially for the Einstein rule that I would call also Einstein metric. And as such, as a logarithmic one, it should be renormalizable. But I am opening for question if someone has Rogério.
Yes, I have a question, Rodrigo. That's great work. So this point source, gamma ray source that you guys found, this was not known before, and also, do you have a spectrum for this emission? Is this can it be a line source, or you have the spectrum already? And I think these are the questions.
Mm-hmm. Thank you for the questions, Rogério. The source, the fact that there was a bright source at the center, a bright gamma ray source at the center of our galaxy is not something new. So this source was already found with Cherenkov observatories, and it was also found with Fermi. Okay, before I started working on this subject, there, right when the telescope was already flying, when the telescope was already on orbit, we knew that there was a source. The novelty here is that we did, this is one of the first thorough analysis of the properties of the source. Okay, so this is the new, we knew this is the news here. We knew that there are photons coming from there, but we are one of the first groups to do a thorough analysis and modeling of this source, okay? And we are the first to show that there is a very promising physical association between this source and Sagittarius A star, number one. So your second question, the spectrum, yes, we have a spectrum. This is this work is under wraps, because this we will share the spectrum and the models with you once we posted the publication on arXiv. It's a beautiful spectrum. I'm very excited about this, and the spectrum is giving us a strong evidence of a hadronic origin for the emission from this source. But I cannot show you now the spectrum because this work is under wraps in the context of the Fermi LAT collaboration.
Okay, I wait for lunch tomorrow.
Okay.
Any further questions? Okay. We can always remind that we have questions after the poster section in the Paredon. Okay, thank you very much. And now Jacques Lepine is going to talk about an update of the LLAMA radio telescope project. Where is Jacques Lepine? He's not there.
No, he's here, but And he's a co-host. So
do you hear me?
yes.
Oh, okay.
Do you see me? Okay,
We can see only the top of your head. Perhaps you could close a little bit the screen.
Okay.
It's much better. So please, let's start then your talk on the update of the LLAMA project.
Yes, and let me see. I have to share the screen, and this is something that I am not very used. Oh, I have it here in my front, but what should I do to?
Do you see a green button in the bottom? Yeah. Say share screen. You have to click that button. Share screen. And then
at the bottom,
a green button. Let me see.
It's written.
It is written on it. Share screen.
Share screen. Yes.
Okay. Well, I am in the Zoom and stop video more. No, more. Share screen. Okay. Do you see any screen?
You see your screen now.
Yeah, it is a PowerPoint.
No, we see the Zoom. We see the we see.
We see the screen of Zoom screen, but now you put your talk, which I don't know where it is.
Well,
yes.
There it is.
Yeah. Okay.
Put the full screen now in the top.
In the top.
No. Just go to presentation mode. Just go presentation mode. It's okay.
Inside the thing. Okay.
Yes.
Presentation.
Yeah. Yes. Yes. Perfect.
Okay.
That's it.
That's it. Okay. It is a relief for me because very often I spend a lot of time on this. So I can start now?
Yes, please. Right away.
Okay. I am going to talk about the radio telescope update. An update is needed because let's say it is a long time that we are working on this project, but it was somewhat stopped for some reasons, and now we are, let's say, starting again. And well, we have this is a project led by the University of São Paulo, by IAG, but we have strong collaboration, for instance, at Mackenzie University, where there are many, and it is a joint project with Argentina, MINCIT, Ministério de Ciência e Tecnologia. Now here, one of the logo is INVAP, and I will tell you that, let's say, the Ministry of Science of Argentina decided to elect this company. INVAP is a company, a very strong company, which is located in Bariloche, with many people working in managing and in let's say technical parts, and they made a contract with MINCIT to go on with the construction of the antenna. So this is why we are now in a new world. Well, we are constructing a radio telescope which looks like this one, which is APEX, installed in Atacama. APEX is a European radio telescope. It belongs to ISO and to Sweden and one more, and it is saturated in the sense that there is a lot more of people asking for observing time than available time. But let's say diameter is the same. LLAMA is a 12-meter diameter radio telescope. So it is a parabola like this one, and it is installed at 4,800 meters. It is important to mention the context of ALMA, because ALMA, you of course know about it. It is the most important radio observatory in the world, and it is maintained by United States, Europe, Japan, and in the north of Chile at 5,000 meter altitude. And there are 66 antennas, 12 meters diameter. And the frequency bands goes from about 100 gigahertz to 800 gigahertz. And we call this terahertz region, let's say, because it includes 1 terahertz. It is terahertz is from 0.1 terahertz to 10 terahertz. And the ALMA is an extraordinary instrument. There are spectacular results going out of it every day. I don't know if you can see, because it is behind the photos here, but I showed, let's say, a protostellar, protoplanetary ring, the place where the planets are forming around a star, and you can see it very, very clearly. In the past, it was not possible to observe this. So this is our radio telescope. It is based on the same design of the, let's say, ALMA antennas, because half of the ALMA antennas were constructed by this company, Vertex Antenna Technique. And we purchased one, but the ALMA antennas do not have this Nasmyth cabin on each side. They only have, let's say, the Cassegrain cabin. So we have, in addition to the Cassegrain cabin, 2 Nasmyth cabins, which offer a lot of possibilities to receive instruments. Well, the aim is to reach the aim by Vertex company, 25 microns RMS fluctuation errors on the surface. But with a better adjustment, let's say ALMA also provides this normally, we will be able to go to 15 microns RMS. This is frequencies, let's say, if these errors can be 1/20th of the wavelength, this means that we can go to terahertz. Here is where, let's say, LLAMA is. LLAMA is, you see, very close to ALMA. And ALMA is in Chile, and LLAMA is in Argentina. The border passes here. And we are at the same latitude of São Paulo. This is, let's say, the tropic. The tropic passes in São Paulo and passes in Antofagasta. So it is just take your car and go along the tropic, and you arrive there. It takes, by car, it takes 3 days to go. But, well, you can take a plane. Another important radio telescope is shown here in the south is CART. It is a Chinese-Argentinian radio telescope. It is a bigger radio telescope. It is, let's say, 40 meters, but it doesn't go to the same frequencies. Let's say it is for frequencies of the order of 50 gigahertz, things like that. So why altitude is so important? Here you can see the atmospheric transmission as a function of frequency. And you see that there are a lot of absorption lines which are due to water vapor that goes to zero transmission. even at the site of LLAMA. But let's say at the site of LLAMA, we will be able to observe it around in these bands, which, for instance, 700 gigahertz. We have a receiver for this. So it is a quite high frequency. They say these different curves, black, blue, and red, correspond to different content in water vapor. So water vapor, it is what makes it difficult to observe in such frequencies. But such frequencies are so interesting that we have to go there. Let us talk a little about the competition of radio telescopes. Of course, we cannot compete with ALMA, the first one of this list, since it has 66 antennas, and it is a quite high site. Apex, the other one that I showed to you, is also at 5,000 meters. And it is also at 12 meters like us. There is a Japanese radio telescope, ASTE, which has a 10 meters diameter. It is a good altitude too. And then comes LLAMA. LLAMA, well, 12 meters, and this altitude is about the same of ALMA. One characteristic of it is that it is able to point to the sun. The other radio telescopes cannot do that because, let's just say, when the light is reflected and go to the subreflector, this melts the subreflector. But in our case, it was slightly depolished so that the light is scattered and does not concentrate. But the light, but the radio waves, let's say the terahertz waves, yes, they concentrate. In Mexico, you have a 50 meters radio telescope at a good altitude, but this 50 meters does not have the precision required for sub-millimeter observations on all. Only a small internal part is good for these frequencies. And then a small radio telescope, Nanten in Chile, which is operated by Japan and Korea. So there are not so many radio telescopes at such altitude, let's say. Now, you possibly are thinking, well, but if ALMA has so much power, what to do? Why have another radio telescope, a smaller one? There are many aspects of science that you can do very well with a single dish radio telescope instead of being, let's say, an interferometer. But there are some advantages. I will talk about that, to be close to ALMA, because we can, at some time, we could be considered as an extension of ALMA. If ALMA wants to get better than it is, it has to put more radio telescope at more distance, let's say 100 kilometers instead of 20 kilometers. Then you get a tremendous angular resolution. And we are, well, let's say, the first to try to have a radio telescope in Argentina instead of Chile. Well, our radio telescope has a double sad story. It was constructed by the Vertex company and was sent to the harbor near Buenos Aires, Zárate, and then, let's say, it had to be there waiting for a long time due to bureaucracy and this this was very costly to pay this, let's say, just keeping a big volume in a harbor. But once the transportation started, an accident with one truck happened. Let's say the truck fall in a curve because it was going too fast and the weight over the truck is good. And this made a damage. And well, fortunately, this took about half a year to solve this problem. But and Vertex constructed another piece of that, and I can even show what is the piece here. This is the yoke, let's say, called the yoke, which was now let me say. But once this was repaired, the antenna stayed some 2 years here in these containers at the site. You see already the site was made plain one to make an observatory site. But this was a problem of financial crisis and political crisis in the Ministry of Science and of Argentina, and there was no money to do the next step, which was the construction of a concrete base where we have to mount the antenna. But let's say this is over. After such a long time, let's say, the Argentinians were even wondering if it was still valid to spend money with this radio telescope. And they called a group of specialists, international ones, from Princeton, from INVAP, from University of, and Thijs de Grauw, which was the director of ALMA. And they looked at all the details, all the documents during a long time, and they reached the final document in August 2020. And the recommendation of this external scientist team, I will just say this one. The scientific case was very strong when approved, and it is still just as strong, let's say, because some new things appeared in, let's say, in the sky, in science, that have to be done, and let's say this radio telescope will still be very important for the Brazilian and Argentinian community. But then they say the project is not organized, nor has the necessary details to guarantee a successful completion. This means that let's say, the Argentinian scientists that were taking care of the reconstructions, they were considered that they don't have the capacity to do that. And then the Ministry of Science decided to have a contract with this public-private company, INVAP, which has a high technological level, high management level to take the responsibility of LLAMA until the first light is reached. So now I move a little, but I just give this message. Now it is going. This company is working very hardly, and they have already understood all the difficulties that are there, and this is so that we will have a radio telescope. So what is the science that there is let's say, a lot of science that can be done. In principle, we were thinking as a multi-purpose radio telescope, not a dedicated one. So that, let's say, an astronomer from Brazil or from Argentina can apply for observing time. But there are some aspect of science that should have priority. It was interesting to see the talk by Rodrigo Nemmen talking about the quasars and black holes, and because this VLBI application is really what will produce very good science. Let's say, what is VLBI? A very long Bayes interferometry. This means that we make use of radio telescopes that are very distant, maybe a few thousand kilometers one from the other, and observe at the same time and keep the signal with, let's say, also a time inscription. So we need a very, very good measure clocks for doing these experiments. It is an expensive experiment, but with this, we can, let's say, be a member of EHT, the Event Horizon Telescope, and even millimetron, which I am going to talk about these possibilities. Another area of science which is very important is astrochemistry. We have the possibility of identifying many new molecules. New molecules are being discovered, and we are on the way to understand how the complex molecules form, and possibly how the life forms in let's say, atmospheres of stars around which the planets are forming. And a third topic that I will mention here is solar physics, to understand the physics of the solar activity, of the solar spots, why these solar spots disappear at some epochs, and let's say this has many things to do with the climate on the Earth. The ozone hole, for instance, is due to the UV radiation. So if the UV radiation changes, this makes a difference. And we want to understand the climate of the Earth, let's say. But let's go back now to step by these possibilities. This illustrates VLBI and EHT, Event Horizon Telescope. Rodrigo Nemmen just talked about that. You can see that these are the lines.
Jacques,
yes?
You have 5 more minutes.
Only 5?
Yeah.
Okay, so I will not talk about that. I will talk about millimetron. Millimetron is a space radio telescope, which is being constructed by the Russians. Let's say if the Earth is a little small, and if you want to have very long bases, you have to put a radio telescope in space. And this we are doing, and the launching is in 2029. Let's say the molecular complexity, I just showed you that there are plenty of lines, plenty of molecules, and it will be very important to do molecular survey and to understand the formation of stars. Now that we know that the formation of stars coming in filaments in the galaxy. And exoplanets, let's say, we are in the epoch in which we know that there is at least 1 planet per star. So there is no star without planets. It's a huge amount. So that this is good for research for life. And research for life, it's, let's say, this interferometry also can help. Solar observations. Well, I already told you about the solar observations. So just talking a little about the technical aspect. Under the radio telescope, you can have mirrors to send the signal to one cryostat, to the other cryostat. And this is the mechanical parts of the let's say, that have been constructed. This has already been constructed in Araraquara. I show you some views of this. It is it has to be very precise mechanics, and you can see that the Alpha Engineering team in Araraquara is very happy to have constructed this, which holds the cryostats here, and this was just below the dish, and a lot of pieces to be able to introduce these previous pieces into the radio telescope, because the Cassegrain cabin has a small cabin, a very small door. We have to incline this to enter. There is a set of calibration loads to transform the signal that we get into kelvins, which is the unit used by radio astronomers. Here we have a optical telescope system with a hole here, because when we start pointing with this antenna, when the antenna is brand new, you have to adjust the constants that are in the tracking program. So you observe with an optical telescope, and you get an image of visible stars that are standard position stars, astrometric stars, and then you know what are the errors. And here is the subsystem holography. You see, you use, this is in ALMA, you use a transmitter which sends radiation to a radio telescope, and the radio telescope reflects this radiation. And then at the focus of a radio telescope, you get this signal which comes directly from the transmitter and the reflected one, and you compare the phase, and then you discover what are the errors in the surface. And then you send guys with screws, drivers, and adjust each panel one by one to reach that precision. These are the receivers that they are ready. One is band 5 and one is band 9 of NOVA. They were built by the NOVA laboratory in Groningen. We have a very strong contact and collaboration with this NOVA. And let's say the software is also quite a big task, because let's say the radio telescope will be controlled at a distance, not by people in the radio telescope. Due to it is difficult to stay long times at this altitude, 4,800 meters, and so the software has to monitor everything. The gain of every amplifier, the temperature and the vacuum, and it has to take care of the, let's say, of the pointing, to take care of the data acquisition, data storage, sending the data to another place. So it is very complicated. We use part of the ALMA programs, ALMA Common Software, which is a great help, but the documentation of these things are not good. And so one of the perspectives, now it is my last slide. Don't get impatient.
I'm tranquil.
With the arrival of this INVAP company, we can talk about time schedules, but they start to make sense. So that we believe that indeed we will have the first light of this radio telescope in 2023. We are working at full steam in Brazil too to make this happen, because you have seen a lot of things we do in Brazil, and we have. we are very grateful with Nova, who has provided receivers, and we have a new collaboration that started. We used to collaborate with Ricardo Finger from Universidad de Chile, but now we are going to construct one more receiver, another band 2+3, two bands in one receiver. And well, in future, we know that we need to have more outreach activity because we work a lot and we don't have time to make outreach and to take care of young people and all that. But we are sure that it is important. So thank you. I finished.
Thank you very much. That was a very nice exposition of what you're doing in this radio astronomy business. Let me ask you something. Do you have people talking about gravitational astronomy in your group?
Well, not directly. No. Let's say we were trying to bring an important scientist that Rodrigo Nemmen knows, is Ciriaco Godi. We asked a fellowship for young jovem pesquisador FAPESP, and they don't give a final answer. But we don't. What do you call gravitational astronomy? It is to look for, because the interaction between stars or things like that, it is gravitational, and we are always ready.
Yeah. But what I mean is that you have this new process of observing very massive objects emitting waves, and this is going to interfere with your optical observations, I guess.
Yes, it may interfere. It was a way that we were, let's say, thinking of for measuring the distance of neutron stars, or because let's say the pulses of the pulsars, they arrive in a rhythm that sometimes is perturbed, and it seems that it is due to this kind of gravitational wave passing. But in reality, we do not have people really working on that.
Do you think it's not convincing yet?
Yes, it is. You know, there is so many things in science to look at, but it is difficult to become convinced of this kind of things. This requires reading many papers and thinking about them. Yeah, and me and the other people who are working in this instrumentation, it is so time-taking that we are not. Well, myself, my science, I work in galaxy dynamics. Let's say around the sun, there are stars with there are kind of winds of stars going in one direction, the other direction. They call this the moving groups, and we are, let's say, with my colleagues from IAG and others, finding good explanation in terms of resonance, the co-rotation resonance, because the place where the sun is in the disk of our galaxy is exactly where the stars rotate with exactly the same velocity of the spiral arms. The spiral arms rotate. So these are gravitational interactions, but I don't know if we can call this gravitational physics.
All right. We have two people wanting to ask you a question. Please, John Braga, could you make a point?
Hi, Jacques.
Hola, João.
Nice to see you.
Nice to see you.
long time we don't talk. I understand that INPE is also involved in LLAMA project. You haven't mentioned that in your talk.
Yeah.
But my question is, it would be nice if we can set up some arrangement that LLAMA can look at some bursting events that we detect with the X-ray missions that we are planning to have on satellites such as NanoMirax or Mirax, or also the Bingo telescope that the Alex group is working on, because they can detect fast radio bursts, and it would be nice to have some automatic setup in which LLAMA can point to these detections, of course, if they occur, so that we can rapidly look at these regions of the sky and see if LLAMA can see some radio counterparts of these detections.
I would mention with you, but maybe instead of LLAMA, there is another project that we were doing. It is the EVIA project, because let's say there are a lot of antennas in South America, in Peru, Colombia, Mexico, that are antennas that were used in the past for telecommunications. And these antennas are not used anymore. And we in Brazil, we have also, we have in Rio de Janeiro state and in São Paulo state, in Morungaba. I entered in contact with the, let's say, the president of this company, which owns the company, the radio telescope in Brazil. I even went there, and this gives you the possibility of let's say, it is not expensive project, because the antennas are there. You don't have to buy a new antenna, and the receivers are low frequency, let's say 8 gigahertz. So we would like to go on with this project, and it is not only me, let's say, Jean-Pierre Rollin from Mackenzie is very interested in that, and other people. But of course, I would like to have a stronger collaboration with INPE, because the collaboration with INPE, let's say, started with Joaquin, because he's a radio astronomer about the same frequencies that we are working. But he's very busy, and he says that, let's say, he does not get authorization from INPE, because we were trying to have a kind of agreement. When the director of INPE was Galvão, we were going in this direction, but this agreement that let's say, we proposed, it stopped somewhere, and we are unable to, let's say, to make it go ahead. Do you think that it would be good to have a kind of formal agreement, or just a collaboration?
I don't know. We can talk to Clésio now and see if you can renew this agreement. I was just wondering that. I don't know. Joaquin is head of the space weather program, so he's
he's very busy. I talked with Alessandro Vinci, because, let's say, these frequencies that we are talking of.
I know the LLAMA is very high frequency. So
So, but let's say the frequencies of the radio counterparts, if he detects one with Bingo, it will be very natural to look at almost similar frequency with the other set to start, and before going to.
But this is very interesting to use these antennas for search for these counterparts. Okay. Thank you very much.
Thank you.
Rogério seems to have
No, I can ask later. It's very really late, and I'm getting hungry.
Okay. So we thank you very much, Jacques, for a nice talk. And we adjourn again after lunch for the sequence of talks with the chair, Marcelo Rebouças. Thank you very much. See you.
Thank you.
After lunch.
All of you.
Thank you. See you.
See you.